In part 6 of this video series, we looked at some small-scale work on the mini mill. In part 7, I want to look at some larger work and explore the maximum capacities of the mill. On the left-hand side of the head, there is a specifications chart that shows the maximum capacities, and I've marked them here on this workpiece. And in fact, I cut this workpiece to represent the maximum X and Y range of movement of the table. So in the X direction, that's 300 millimeters or 11.8 inches. And in the Y direction, it is 130 millimeters or 5.1 inches. In the Y direction, the range of table movement is actually greater than the width of the table itself. But in the X direction, the maximum range of movement is actually less than the length of the table. And that's because the table needs to have some extra room on either end in order to move a workpiece over to the center without bumping into the end of the table. As an illustration, I've marked the center of this simulated workpiece and I've lined it up with the center of the table. And now we'll crank the table all the way down till we bring this end of the workpiece under the spindle. I've mounted a 1/2 inch diameter spud in the collet just to simulate an end mill. And now as we're approaching the end of the table, you can see we just barely have enough clearance there to reach that end of the workpiece. Now let's move the table all the way to the back and see where we end up. That's about as far as I can go. The movement of the y-axis towards the back of the machine is actually limited ultimately by the sensor for the x-axis DRO, which is mounted back here. You really don't want any pressure to be applied to this because it's a fairly sensitive and precise device. That does not move back and forth with the table. The table moves independently of that, so at least you're not going to be dragging it along into the dovetails or something. Now with the table all the way forward, you can see we haven't yet reached the back edge of the workpiece. That's because the specification of 5.1 inches or 130 millimeters is actually the range of table movement without the DRO sensor back here. But by adding the DRO sensor, you lose about an inch of movement in the y-axis. But I think it's a pretty fair trade-off given all the advantages that the DRO brings. But that's important to know if you're thinking about buying a machine and you plan to use workpieces that are close to this maximum size. In some cases, you can stretch the limits a little bit by offsetting the workpiece. So for example, you might set it closer to the right end and then mill as far as you can, and then offset it towards the left end to do the remainder. Of course, when you do that, you have to use a dial test indicator to make sure that everything is square with the table throughout the entire operation. Most of the smaller parts made on the mill are held in a precision milling vise. It's also fairly common to have a larger workpiece like this 1/2 inch thick plate, which is clearly too big to fit in the vise. In that case, you can remove the vise and you can position your work directly on the table. But in practice, you wouldn't put it on the table because you need some clearance to be able to cut down the edges. So during an actual job of this type, you would use spacers underneath. This is one type of spacers that are frequently used. These are referred to as 1, 2, 3 blocks because the dimensions are 1 inch by 2 inches by 3 inches. So we have a pair of these, and these are sold in pairs that are accurately matched so that the heights are very accurately matched to each other. So if you wanted to machine the front edge of this plate, you might set it on top of these 1, 2, 3 blocks and then use clamps to hold it down tightly to the table. There are various types of clamps that can be used, and these are some really nice ones made by a company called A to Z CNC. But I was looking for some more of these recently, and it looks like they may no longer be available. A much more common type of clamps is this clamping kit here that has sort of like an erector set of parts that you can pick and choose what you need depending on the physical dimensions of the workpiece that you're trying to clamp to the table. They have these little step blocks that can be used to stack things so you can clamp them at various heights. And then you have different lengths of screws and different lengths of these clamps. The advantage of these clamps is that they're very versatile. You can use various parts to clamp down just about any shape you can imagine. But this is just a simple two-dimensional plate. I'm setting up here to mill on this front edge to clean up this rough bandsaw cut surface. Before I start cutting, I want to adjust this plate so that it's pretty close to parallel with the movement of the table. That way I don't shave off a bunch of extra metal unnecessarily. So to do that, I'll use a dial test indicator. I'll bring that into contact with this front surface, and then by moving the X-axis hand wheel, I can tell by the movement of the dial the degree to which this workpiece is parallel or not parallel with the table. So with the two clamps just tightened down finger tight, I can tap on the corners of the plate with a small hammer to bring it into alignment. You can now see that as I move the workpiece along the X-axis, that there's relatively little movement. Most of the cutting you'll do on a mill is done by these end mills, and they're called end mills, I guess, because they cut on the end as well as on the sides. But this is a typical set of end mills, and you can see these are in inch units, and they're also available in metric, of course. And they go from 3/16 all the way up to 3/4. Now often the shank diameter, which is this part here, will be the same as the end mill diameter. But in some cases, like this one, the shank is smaller than the diameter of the cutting head. And for these small diameter end mills, the shank may be larger than the cutting flutes. To hold the end mill securely while cutting, it's typically held in a collet that slides in there, and then as the collet is drawn up into the tapered head of the mill, this flexible area here clamps down very tightly around the outside of the end mill while keeping it exactly centered with the axis of the mill itself. So we're almost ready to begin cutting now, except we need to move the cutting tool down so that it's at the level of this front edge of the work. And I'll use the 3-spoke hand wheel to move the head down until the tool is down a little bit lower than this front edge. And then I'll lock the hand wheel, and I'll use this other locking lever. This makes sure that the head cannot move up or down during the cutting operation. Now, one problem with using collets to hold the end mill is that the head must be down pretty far and close to the work. And you can see in this case, the end of this handle here can interfere with the work. So I'll need to temporarily remove this handle so it won't obstruct the movement of the work. I'm going to use a 6mm wrench, and there are some flats here that you can grab with the wrench. And once you loosen that, you can just turn this off. Another way you can avoid this problem is, instead of using a collet to hold the end mill, you can use an end mill holder. The advantage of these is they let you keep the head about 2 inches higher, so you aren't right down on top of the workpiece as I am in this case. The disadvantage to these is they're fairly expensive, a lot more expensive than a set of collets. So most beginning mill owners get the collets first, and then the end mill holders are something you can get later if you find that you need them. All right, now we'll turn the motor on. The rotational speed isn't critical, and for right now I'm going to set it to about 900 RPM. And you'll find as you get experience that you have a pretty good idea what speed is appropriate for the work you're doing. But on this mill, of course, you have a tachometer, so you can set the speed to exactly what you want and know exactly what speed you're using for future reference. I think I'm going to increase that spindle speed just a little bit to about 1,000. One of the nice things about the mini mill is that you can adjust the speed at any time. So if you hear or see that the cut's not going quite the way you want, you can make adjustments to the spindle speed whenever you want to. So as I turn the X-axis hand wheel, the work is moving to the left and into the cutter. It's time to introduce the little finger, and those of you who are longtime viewers of my channel, this is a very popular tool that I use for pointing out details. The edge here is now a lot smoother than it was before. You may be able to see that there's some vertical lines here, and those are places where I stop the movement temporarily in order to make adjustments. Now, when you're cutting into the turning flutes going in that direction, that's called conventional milling, and that is typically used for your initial cuts. But you can actually get a smoother finishing cut by moving the work back in the opposite direction. And also, if I increase the RPMs, that will make a smoother cut as well. So that's just to give you a sample of some of the types of milling that you can do on a long workpiece using a clamping setup. Of course, if we were making a finished workpiece, we'd now have to remove the workpiece and flip it around 180 degrees so that we can mill the other side. We also have to make sure that the ends are square. Now, the problem, of course, is we want to mill this edge here, but this clamp is right in the way of where we need to work. So the first thing I need to do is move that clamp, but in doing that I have to be careful not to shift the work or this edge will not be milled square to this front edge. So what I've done in this case is I very carefully loosened this clamp and I moved it from the front slot here to the rear slot, so now I can access the front half of this edge. Then after I get that done, I can move it to the front and do the back half. So it's awkward, but on a small mill like this, in a workpiece that is close to the limits of the mill, you sometimes have to get creative with your the way you set things up in order to reach all the corners you need to reach. But let's go ahead and start it up and take a look at milling that edge. And now I'll lock the x-axis and use the y-axis hand wheel to cut towards the back. So the table's moving forward and moving the workpiece into the cutter. When I get as far as I can get without hitting the clamp, I'll stop and move the clamp. Now, a better way to do this is to use a third clamp, as I've done here, so that I still have two clamps holding the work while I'm moving this third clamp out of the way. For extra safety, when you're working up close to the cutter like this, you can use the spindle lock to temporarily cut the motor off so you don't have to worry about accidentally hitting the button on front and starting up the cutter. So now I'll start up the mill and we'll finish that cut. And here again, I'm just about at the limit of the y-axis movement. So this plate is about as big as I can mill in one pass on this size mini mill. Well, that wraps up our exploration of milling larger workpieces on the mini mill. If you're new to the world of mini mills, I hope you found it informative and learned some things along the way. If you're a more experienced machinist, I appreciate your tuning in. So until the next episode, enjoy your time in the shop. Thanks for coming.